Hello, good morning, and welcome to the chemistry lecture on the topic gaseous state. Today I am going to explain about gaseous mixture, Dalton's law of partial pressure, and then we are going to solve some problems based on Dalton's law of partial pressure. So consider here, this is a glass flask having 1 liter capacity. This is 1 liter flask, another flask. The two flasks are connected by glass tube, and here is one valve or one cork. This flask is also fitted with a funnel having a cork, or you say cork or cork or follow. In this flask, 1 liter helium is taken. In this flask, helium is filled up to 152 mmHg. This valve or this cork is closed. This valve or cork is also closed. In second flask, hydrogen is filled up under 608 mmHg pressure. The flask is filled with hydrogen to a pressure of 608 mmHg. Helium and hydrogen are non-reactive gases. So the pressure exerted by helium is 152 mmHg. The pressure exerted by hydrogen is 608 mmHg. These corks or valves are closed. Now you see, a mineral oil is poured from this funnel, and this cork is opened. Similarly, this cork is opened. The oil enters in this flask, and helium through this glass tube enters in second flask. Continue the adding of mineral oil till it is completely filled and all helium is entered in this flask. When this flask is, this is rubber cork, here is rubber cork, airtight cork. When this flask is filled with mineral oil up to this, close the cork, this cork close, all helium is passed through this tube and entered in this 1 liter flask containing hydrogen. I represented hydrogen molecules like dot, and helium molecules are hollow spheres. So helium enters here. Hydrogen and helium are non-reactive gases. Non-reactive gases. So this is simple experiment. In one flask, helium is filled up to at 152 mmHg in 1 liter flask. In another liter flask, hydrogen is filled at 608 mmHg. Both the gases are mixed. Both the gases are mixed. We try to understand what Dalton had observed. Dalton observed that each gas, that means helium and hydrogen, exerts the same pressure if other were not there. Helium and hydrogen exert the same pressure in this flask also if there is no any gas, if there is no other gas. I explain it. In this vessel, two mixtures of gases. So, pressure exerted by helium, pressure exerted by helium is equal to 152 mmHg plus pressure exerted by hydrogen is equal to 608 mmHg. Total pressure of the gas, total pressure of the gas or of the mixture is equal to total pressure of the mixture or of the gases in the mixture is equal to, it is found to be 152 plus 608 is equal to 152 plus 608, that is equal to 760 mmHg. So it is Dalton's observation. So when hydrogen and helium are separate, they exert a particular pressure on the walls of the container. When they are mixed, they also exert the same pressure on the walls of the container. On the walls of the container. Pressure exerted by a particular gas in a mixture is the partial pressure of that gas. I repeat once again. Pressure exerted by a particular gas in a mixture is the partial pressure of that gas. In this example, partial pressure of hydrogen P of helium plus P of H2 is equal to partial pressure of helium is 152 mmHg, partial pressure of hydrogen is 608 mmHg, that is equal to total pressure of the mixture. Total pressure of the mixture. This is Dalton's law of partial pressure. Pressure exerted by a particular gas in a mixture is the partial pressure of that gas. So, I clean the board and I give you some more explanation about Dalton's law of partial pressure. Suppose there is a mixture of different gases. Mixture of different gases A, B, C, etc. If PA is the partial pressure of component A, PB is the partial pressure of component gas B, PC is the partial pressure of component gas C, then total pressure exerted by the mixture of the gas is given like this: P total is equal to PA plus PB plus PC plus PC plus etc. So this is Dalton's law of partial pressure. Is it clear? If it is clear, I am going to explain one more next point. You know that ideal gas equation PV is equal to nRT. nRT. This is ideal gas equation. So, I write for component A, partial pressure A into Phi is equal to moles of gas A into R into T. That means ideal gas equation is also applicable for each component of the gas. For each component of the gas. Therefore, PA is equal to NA RT upon phi. Or you write like this: NA RT upon phi. At constant temperature and constant volume, partial pressure of gas is proportional to moles of the gas. Here I write proportional to NA. So try to understand. R is gas constant, it is fixed. When volume is constant, temperature is constant, R into T upon phi, constant multiplied by constant divided by constant is another constant. Therefore, I wrote PA proportional to number of moles. Partial pressure of component A gas is proportional to moles of A. Then I write the same equation: PV is equal to nRT. Mole fraction. This is another important term, mole fraction. In problems, we are going to solve how to calculate mole fraction. Mole fraction is the ratio of moles of component A divided by total number of moles of the gas mixture. Total number of moles of the gas mixture. So this is mole fraction. It is calculated like this. It is the ratio of moles of that component divided by total number of moles. When we solve problems, it will become more clear. Then mole percentage or mole percent is equal to mole fraction into 100. Mole percent is equal to mole fraction into 100. Sometimes this mole fraction is denoted like this, XA. So whatever I explain, what is a gas mixture of unreactive gases, non-reactive gases, hydrogen and helium. Partial pressure definition, mole fraction, mole percent, and mole fraction and mole percent. I think up to this point it is clear. If it is clear, we solve some problems on this type of formula. Dalton's law of partial pressure. Pressure exerted by individual gas of the mixture. Pressure exerted by the mixture is the sum of individual pressures or partial pressures of the components of the gas. So first we solve example 5.10. I write the example, a 1.00 liter sample of dry air, at 25 degrees centigrade contains 0.925 gram nitrogen plus other gases including oxygen, argon and carbon dioxide This is given A. What is the partial pressure? What is the partial pressure in mmHg, in mmHg of nitrogen in the air sample, in the air sample, and B, what is mole fraction and mole percent of N2 in the mixture. This is the problem. 1 liter sample of dry air, that means volume is given. Volume is equal to 1.00 liter. For simplicity, I write 1 liter. Same, it is same. At 25 degrees centigrade. So T is equal to 25. Convert degree centigrade into celsius, Kelvin scale, plus 273, that is equal to 298 Kelvin. 298 Kelvin. The weight of nitrogen is given. Look here. Mass of N2 is equal to 0.925 gram. And other gases also present in the mixture, that are oxygen, argon and carbon dioxide. So nothing is concerned about these gases because the problem is related to nitrogen only. So mass of nitrogen 0.925 gram. What is the partial pressure of nitrogen in the air sample? Partial pressure P of nitrogen is equal to dash mm of Hg. We have to calculate. Third, what is the mole fraction? Mole fraction N2 is equal to question mark. Mole percent that is equal to question mark. This is we want to find out. Now I calculate first mole of N2. How will you calculate mole of N2? Atomic weight of nitrogen is 14. Molecular weight of nitrogen M of N2 is equal to, nitrogen is diatomic molecule. Atomic weight of nitrogen is 14 divided by is equal to 14 plus 14, that is equal to 28. That is equal to 28. So Na, number of moles of N of N2 is equal to mass of N2 divided by molar mass of N2 is equal to molar mass of N2. So mass of N2 is 0.925 divided by molecular weight 28. Solve it. That is equal to, the answer is 0.0330 mole of N2. From ideal gas equation, I write PV is equal to nRT. Partial pressure of nitrogen we have to calculate. So Pn2 is equal to Nn2. Therefore, partial pressure of nitrogen is equal to moles of nitrogen 0.0330 into molar gas constant. It is constant. You know its value 0.0821 into temperature 298 Kelvin. Substitute there, divided by phi, volume of nitrogen. 1 liter, because 1 liter sample of dry air divided by 1. Solve this, simplify this. The answer is 613 mm of Hg. 613 mm of Hg. Simplify this by using calculator. So convert this mmHg into, we have to calculate into mmHg, but you see the answer is 613 mmHg. To convert into atmosphere, divided by 760, that is equal to 0.807 atmosphere. 0.807 atmosphere. This is the second step. Then what is asked? Mole fraction of nitrogen. Mole fraction of nitrogen. So, X of nitrogen, mole fraction of nitrogen is equal to number of moles of nitrogen divided by molar mass of nitrogen. Number of moles of mixture, that is equal. But we don't know number of moles of mixture. This mole fraction is also proportional to partial pressure of nitrogen to partial pressure of the mixture. So that is equal to partial pressure of nitrogen 0.807 divided by pressure of the mixture, that is equal to, how will you calculate the pressure of the mixture? Here one thing is missing. A 1 liter sample of dry air at 25 degrees centigrade. Here it is provided, I forgot to wrote, divide and 786 mmHg. So divided by 786 atmosphere. So instead of taking here atmosphere, this pressure is given in mmHg. So you take here also mmHg 807, that is equal to 613. The answer is 0.780 mole fraction. It is a fraction, therefore it has no unit. Mole percent, calculate mole percent is equal to mole fraction into 100 multiply this value by 100, that is equal to 78. This is mole percent. So this is the answer. This is solved example in your textbook. After completing this, we are going to solve one more problem, exercise number 5.10. After solving this problem, we are going to stop today. One simple problem. One minute. Exercise 5.10. A 10-liter flask contains 1.013 gram of O2 and 0.572 gram CO2 at 18 degrees centigrade. What are the partial pressures? What are the partial pressures of oxygen and carbon dioxide? What is the total pressure? What is the total pressure? what is the mole fraction? What is the mole fraction of oxygen in the mixture question mark. Read the problem carefully and write down the given quantities or the given data. So a 10-liter flask, that means volume is given, phi is equal to, instead of writing 10.0, for our simplicity I write only 10 liter. Mass of oxygen is given, m is equal to 1.013 m of O2. Mass of carbon dioxide is also given, m of CO2 is equal to 0.572 gram. Temperature is given, T is equal to 18 degrees centigrade. Convert into Kelvin by adding 273. 8 plus 3, 11. 7 plus 1, 8. 281. Am I right? Sorry. 8 plus 3, 19. 7 plus 1 plus 1, 291 Kelvin. We have to calculate what are the partial pressures of oxygen and carbon dioxide. P of O2 is equal to question mark. P of CO2 is equal to question mark. Mole fraction of oxygen, X of O2, we have to calculate. That is equal to question mark. So, solve this problem. First, according to the equation PV is equal to nRT. We want to solve this equation, this problem by using this relation. So, first calculate moles of O2. N of O2 is equal to mass of O2 divided by molecular weight of O2, that is equal to mass of O2 is 1.013. Calculate molecular weight. You know atomic weight of oxygen is 16. Its molecular weight O2 is equal to 2 into 16, that is equal to 32, divided by 32, that is equal to number of moles. The answer is 0.031 mole. Similarly, calculate moles of carbon dioxide. N of CO2 is equal to m of CO2 divided by molecular weight of CO2, that is equal to mass of CO2 0.572 divided by, calculate molecular weight of CO2. Atomic weight of carbon is 12, oxygen is 16, another oxygen 16, that is equal to 44. Solve this. The answer is 0.013 mole. 0.013 mole. I want some space, so try to write here. PV is equal to nRT, PO2 into Phi is equal to NO2 into RT. Therefore, PO2 is equal to, I take this Phi on right hand side, NO2 upon RT into Phi. Substitute the values. Number of moles of O2 0.031 into 0.0821 into 291 divided by volume 10 liter. 10 liter. That is equal to. Simplify this. The answer is 0.074 atmosphere. Similarly, calculate partial pressure of CO2, that is equal to N of CO2 into R into T upon Phi. Moles of CO2 is equal to 0.013 into 0.0821 into temperature 291 divided by volume 10, that is equal to. Simplify this. The answer is 0.105 atmosphere. Can you solve the remaining problem? What is asked? Mole fraction of O2. So look here, how to calculate mole fraction of O2. I clean here this space. So here, total pressure exerted by the mixture is equal to partial pressure of O2 plus partial pressure of CO2, that is equal to. Partial pressure of O2 we have calculated 0.074, partial pressure of CO2 0.105, that is equal to. Add these two terms, find out the answer. Here the answer is 0.031. That is equal to 0.105. Calculate mole fraction of O2. X of O2 is equal to N of O2, moles of O2 divided by total moles, that is equal to moles of O2 0.031, divided by total moles, that means moles of O2 plus moles of CO2, that is equal to 0.031 plus 0.030, that is equal to, simplify this, the answer is 0.704. This is mole fraction of oxygen. Mole fraction of oxygen. So this is about Dalton's law of partial pressure, mole fraction and mole percent. I have explained each and every point in your textbook. There are some more problems for practice. Solve those problems. Today I am going to stop here. Thanks for watching. We shall meet in next lecture and we study some more points. Thank you so much. Have a great day.